last time, we need to solve our computing problem number 9, greatest common divisor. And we recall the middle school procedure using the prime factorization. Yeah. Although it is, from the procedure point of view, it is simple, but it relies on prime factorization. And later, I explain this prime factorization could be very slow when you need to factorize a large integer. So how large? I use this 1,000 digit example, this large, then it could be as slow as a few months, that slow. Yeah. All right, so that's what we were last time. Yeah. Later, if I have time, I may talk about, this prime factorization, because this slow, here, let me write, prime factorization, very slow. The slow prime factorization, this fact could be useful, in encryption application. Yeah, so that's very interesting. Yeah, later when I have time, I may talk about, this story. Yeah. All right, so let's continue to the next slide. So this time, we need to solve it in a more efficient way without using the prime factorization. Yeah. So that's the goal. Yeah. Right. But how to do it? How to make it faster? How to get around the prime factorization? Yeah. The idea is simple. Yeah. Idea, although here I put a goal here, but the idea is also like this: reduce the problem size. So we have seen different ways to reduce problem size. Here, another way. If you look at the title of this part B, we call it variable size reduction. Variable size reduction. Yeah, so that's what we are going to have. Yeah. To do that, yeah, so you ask the question, how to reduce the problem size? Yeah, that's the critical part. Yeah. To do that, we need to use a mathematical tool. Okay, some special mathematical tool to help us. Yeah, so you may feel, we may need some fancy math tool, but actually that tool is very simple. So what's that? Division algorithm. Division algorithm. How to do integer division? You know how to do, right? Yeah. Everyone knows how to do integer division. And we use that integer division here. And we give it a fancy name called the division algorithm. The integer division is so simple, but people still give it some formal name, division algorithm. Yeah. This name appears in number theory. Number theory. Okay. Yeah. So here we use the number theory version division algorithm. What's that? Given positive integers a and b, b is not equal to 0 because we want to use b as the divisor. The divisor cannot be 0. Yeah. So we can make this assumption, b not equal to 0. Yeah. Then the conclusion part. There exists unique integers q and r. Q for quotient, r for remainder. So quotient and the remainder part. Yeah. With the remainder must be in this range, greater or equal to 0, less than b, strictly less than b, such that a equals b times q plus r. This is the so-called division algorithm. Yeah. So here you can see we just formulate the usual integer division in this way. Nothing fancy here, right? So plain, so simple, but so useful. In number theory, this division algorithm is extremely useful. Okay, yeah. Many advanced theorems are developed by this division algorithm. Okay, yeah. Here, to find the greatest common divisor, we need to use this tool. Yeah. How to do it? Yeah, let's do it. Let's connect A, we replace A by M. We replace B by N. We do integer division. Okay, yeah. All right, so then, yeah, but here we make some small assumption, M greater or equal to N greater than 0. Yeah. If not, we switch, yeah, because you may ask, how about when we are given arbitrary two integers, how about N greater than N, right? We just swap. If that happens, we swap N and M. Then our first integer will be greater than the greater or equal to the second integer. So we will have this assumption. Yeah. All right. Yeah, the reason we want the first integer greater than second one, because for problem size reduction. For the reason is for the problem size reduction. Yeah. Yeah. So what is the problem size here? Now, you may ask that. So what is the problem size for this question? Yeah. In this question, the problem size is the maximum of M and N. So when we do problem size reduction, we want to reduce the maximum of these two numbers. Yeah. All right. Yeah. All right. So here, to do the problem size reduction, so let's start with this version after we apply the division algorithm. Okay. Yeah. All right. So the next step, in order to see how do we reduce the problem size, we need to do transformation on this formula. Okay, yeah. To do transformation, yeah, we start with the GCD of M comma N. That's our goal. we need to calculate this function. Yeah. So when we start, we replace m by this new expression, nq plus r. Yeah, so we get this expression. The question, we want to simplify it. Simplify it. Yeah. Mainly here we see there is a term that is a multiple of n times q. It is a multiple of n. Can we do some simplification regarding this multiple of n? Yeah, we can see it. Let's look at this fraction. Left-hand side m over n. Yeah. The reason we consider fraction, you may ask why we consider fraction here, because we want to do cancellation, right? Yeah. So we want to do simplification. Let's say we want to do simplification. Yeah, not necessary cancellation. Yeah. Simplification. When we do simplification, because m equals to that nq plus r, so the nq multiple over m, we get the quotient n out. Then remainder r over n, that's the fractional part. Q, the integer part. R over n, the fractional part. Yeah. So after this transformation, yeah, this is our transformation, or part of it. Yeah. After that, you can see the integer part would not do anything regarding the fractional simplification. Yeah. Think about it this way. When we do cancellation, this integer part does not have any impact on the cancellation, right? Yeah, that's the integer part. Nothing to do. There is no impact on the denominator, right? Integer does not put any impact on the denominator, right? Yeah. Yeah. From that point of view, so you can see the GCD of m comma n, the same as the GCD of r and m. So that's this one. Yeah. The Q part, new contribution to the GCD. The Q part, the m multiple part has no contribution to the GCD. Yeah. Because the GCD is the greatest common divisor, right? Greatest common divisor, when we do cancellation, we cancel greatest common divisor, right? M over n, if you want to make this fraction as simple as possible, you cancel out the greatest common divisor, right? Yeah. But that Q quotient part, it's an integer. It's integer. The integer part has nothing to do with the divisor cancellation. Think about that, divisor cancellation, okay? So nothing to do with the divisor, so we can remove it. Yeah. So this version, that's the after the removal, integer part removal. So we get a GCD of m, and this time size reduced. The size is reduced. Okay, yeah. The size, this time, size is n. Yeah. Before reduction, the size is m. After reduction, the size is n. And we assume m greater or equal to n. Okay, yeah. So it is reduced, although there is a m equal to n case, but that won't happen frequently. Most of the time, n greater or equal to n. Yeah. All right. So this is the key property. Develop a key property. What is the key property? This is the key property. The problem size reduction formula. This is the key property. Okay, yeah. Now we apply this key property, we can solve this GCD problem. Yeah. Okay, yeah. So we, yeah. And we can keep doing, yeah. This is only one-time reduction. Can we do second time reduction, third time reduction, and so on, until we cannot do it anymore. Yeah. If we can do, we keep doing it until we cannot do it anymore. Okay, yeah. So the algorithm that way, that method is called Euclid's algorithm. Yeah. Euclid, about 2,000 years ago, 2,000 years ago, Euclid wrote a, famous book volumes, yeah, several volumes. So it's just called books, okay? As I remember, yeah. And inside it covers, all the basic math theory, geometry, number theory. Yeah. And this Euclid's algorithm was one of the main results in that book's volume. Yeah. Yeah. All right. So that's just like the rule is as simple as this one. When you calculate the GCD, if y equal to 0, because we do not allow x, y both 0. Remember? Yeah. Remember the condition. Yeah. We do not allow x and y both 0. Yeah. Later I will explain that. Yeah. So here y could be 0. If y is 0, then the answer is x. Okay. Yeah. Yeah. Because we assume x not equal to 0 by the initial assumption. Yeah. If otherwise, yeah, if x mod y, this is modular operator, okay, percent. If x mod y equals 0, that means x is a multiple of y. Okay, x a multiple of y. Then the answer is y. So that's two base cases. Otherwise, problem size reduction. Okay, we put the y as the first variable in GCD. The second variable we use x mod y. The size is reduced in that way. Okay, yeah, and we keep doing this until we get to the base cases. Yeah. Because finally, we need to get to one of the two base cases. So we stop. Okay, we stop. All right, yeah. That's the famous Euclid's algorithm. Famous. Yeah. Very important in number theory. Yeah. This algorithm is important, fundamental in number theory. Okay, yeah. All right. For us, we use this algorithm. We can calculate GCD without using prime factorization. The great thing of this one, without using the prime factorization. That's the best thing we have from this algorithm. Okay, yeah. Then its direct consequence, it will be much faster. It avoids prime factorization. Yeah, think about, even we have 1,000-digit, 2,000-digit integers. Yeah. So imagine 2,000 digit integers. Yeah, we want to calculate GCD of these two numbers. Because by applying Euclid's algorithm, we do not need to do prime factorization. And basically, we just do integer division, modular operation, integer division. That's much faster than prime factorization. Okay? Yeah. So although you need to do many, many times, you know, the size could be reduced quickly. Okay? Quickly. Yeah. Yeah. And you can get your answer very fast. Yeah. It's very interesting. I make a programming project on this one. Yeah, but I may like to make it as an optional. So if it's possible, I make it optional. Yeah, because our formal project, I have another topic for the formal project, you know, the Fibonacci numbers. Yeah. Next, I will go to the Fibonacci numbers. Yeah. Yeah. And this one, it's an interesting problem. Yeah. Not too hard. The thing is, if you need to implement Euclid's algorithm, that's easy. But at the same time, you need to compare it with the prime factorization method. Yeah, you need to do comparison. Yeah. So the prime factorization, yeah. Actually, I have one example, prime factorization. I used it last semester. Okay. So I can give you that example last semester. Yeah. Last semester, when I remember, when I tested, do prime factorization on 16-digit number, 16-digit integer, no, it's not very slow. No, 16-digit, still a few seconds. But larger than that, you know, 20-digit, only 20-digit prime factorization, extremely slow, you know, running forever, never stops. Only 20-digit, not 1,000-digit. Think about the huge difference. Not 1,000-digit, only 20 digits. Yeah, it never stops. Okay. Yeah. I do not have the patience. You know, I have to kill the program. Okay. Yeah. All right. Yeah. So if you are interested, later I can post my program so you can do experiments by yourselves. All right.